All right, this week we're going to talk about optimization under uncertainty. We finished our discussion on surrogate-based optimization last week. There are a few other topics I didn't discuss, but details are in the book if you're interested. I just added recently a lot more detail on kriging, some examples there. And there's also a section on deep neural nets, which we didn't discuss, but which may be of interest to some of you. Today we're going to talk about uncertainty. Uncertainty is prevalent in engineering design, although we don't always address it, and it's something that's increasingly important as we move or work with these complex engineering problems to incorporate in our optimization procedures. So just to give you some examples, so let's say an engineering example, if you go to specify a part and you design all the dimensions, we know that there's going to be some uncertainty in the exact dimensions, right? Manufacturing is going to cause some deviations from the specified dimensions. Material properties are going to have variations. Atmospheric conditions are going to vary. There's a lot of things that are inherently variable. And if we design based on these deterministic quantities, we could have designs that either significantly underperform or have failures. And sometimes this uncertainty occurs in design variables, and other times it's in parameters, things that are not a design variable, for example, the density, viscosity of the air, for example, but still affect our design. So optimization under uncertainty is all about trying to perform optimization while accounting for some of these uncertainties and variability. Just to give you a couple other examples, there's going to be two types that we're going to talk about. Okay, and we'll call it a robust design and a reliable design. I'll define those more in a second. But the reliable one, this is not an engineering example, but maybe something we're familiar with. Reliability is about the constraints. So imagine I am just trying to hop on my bike and go to a nearby park to play basketball. Okay, there probably is not that much uncertainty in how long it's going to take me to get there. And so I may not need to really plan for that. But let's say I want to make a trip to the airport. And if I try to plan to get there, right on time, I kind of figure out exactly how long everything's going to take. I know that that's going to cause me, or potentially could cause me, some real issues, right? There's a lot of uncertainty. I don't know what traffic's going to be like. Maybe it's busy. Maybe there was an accident. Maybe there's some lane closures. Maybe there's a lot of people traveling today. Maybe security has less people and it's taking longer. So I have to add some buffer. If I was to draw a picture, say this is time, and here's my constraint, right? Here's where they shut the gate and I missed the airplane. And if I plan to arrive like right here, that may work if everything just goes according to plan, but in reality, the time that I arrive probably falls under some distribution, maybe, and it's probably not symmetric, but let's say like something like this, right? Here's my distribution of when I'll actually arrive based on planning to arrive right here. And so there's a good probability that I'm going to be late, right? And so instead what I do is I try to put in some buffer and say, okay, let's leave much earlier so that, the probability that I miss it is acceptably small, right? I can never really take that to zero, but I can make it really, really small. Okay, and what really, really small means, I guess, depends on how comfortable you are. We could leave days before, right? And even then, it's not 100%. Something could happen. All the roads could get washed or demolished or something, but the probability could be acceptably small. Okay, so this is about reliability. We say that the design, we'll call it the design, but design just means the outcome of our optimization is less prone to failure under variability the variability that's going to exist. And this is associated with constraints, okay, because that's where the failure occurs. In other words, it means that our constraints are going to be more likely to be satisfied with a higher probability. Okay, a different example about robustness. Robustness, maybe not everyone's played the game Monopoly, but that's the example I could think of. So you're playing Monopoly. Monopoly, is this game, where you move around on these little spaces here. And what happens is you try to earn money and you develop these properties, right? And you buy certain properties and you can put these little greenhouses on your properties. And let's say you own some properties over here. And then if you get a bunch, you can put this red hotel, which is worth more, okay? And so you want people to land on your spots, and then they're going to, have to pay you for those. And the goal is to, try to get all the money, I guess. Anyway, the idea here is that if you had a deterministic procedure, you knew exactly where someone was going to land, right? Then we would put all our eggs in one basket, so to speak, right? We would say, okay, if I am very certain you are going to land on this square right here, I'm going to put everything right here, use all my resources to develop this one. But then if you land over here or here, nothing happens, but I'm very confident you're going to land there. That would be the best I could do, but it's uncertain, right? I don't know. You're going to roll a dice. This game is based on rolling a dice. And so you could land in a bunch of places. So usually a better strategy is to kind of spread these out, right? Put houses on a bunch of different properties. That does mean that at a given moment, I'm going to develop each to a lesser extent. But my design is more robust. Okay, and robustness has to do with the objective. So we could write it this way, that the performance is less sensitive to variability. Okay, and this has to do with the objective. Okay, so that may mean again that any one row I may not do as well, but overall, let's say my average performance is probably going to be better, right? That's the sort of key here. So we're trying to get designs that are going to be less sensitive, that they're going to perform better in some statistical sense. Okay, so today we'll focus on this latter one. I think this is the easier one to get going on. And next time we'll talk about robustness. I'm just going to do real quick a few statistics kind of review things. I'm not going to review much, just maybe a few quick ideas. Okay, one is the probability density function. That's the kind of thing I was drawing. So if I had some variable x, and then this axis, we would call this p of x, then, I have some distribution, and it doesn't need to be symmetric. It's whatever it looks like. This function, this probability density function, or PDF as we call it, tells me the relative probability of any event occurring. Okay, so I'm sure you're familiar with the Gaussian distribution, the bell curve, right? There are tons and tons of different kinds of distribution, infinitely many. There are many that have names, and there are many that, are not. They're just based on your data. Some properties of this, that if I integrate it everywhere, then it has to equal 1, right? Because that means that, 100%, I've covered all the possible probabilities. The probability of, say, let's say this is A and this is B, the probability that X is between A and B, right, is just equal to the integral from A to B. Sorry, this is dx. Okay. So that's what a PDF is. It's very useful for us to get means and variances. Hopefully these are things you remember. The idea, the mean, we also call this the expected value, E of X. The expected value is equal to, this is just the mathematical formula, X integrated across that probability density function, dx. that will tell me the mean of that distribution. Okay. The other quantity that we use a lot is called the variance. And the variance, this is a really ugly looking E. Sorry, I need to redraw that. Okay, that's the expected value. Let me just write that because that's a commonly used word. Expected value. Okay, also known as the mean. This is the variance. Remember, the square root of the variance is just the standard deviation. The variance you could think of, it's kind of like, it's the average deviation. I guess it's not kind of, it is, right? So if I took my deviation, this is my, or deviation from the mean. This is how far a given point is away from the mean. And just like we did with the sum of squared errors last week, I can't just add deviations that are positive and negative. They'll all cancel out. So I want to square all those deviations. And then, if I take this quantity, and I put it here, because this is telling me the average of X. So if I keep everything else the same, this is now, if you compare those two, this is variance you could think of. It's the average squared deviation from the mean. So in other words, it's telling me how spread apart I am. If the variance is small, then things don't deviate very far from the mean. If the variance is large, then they deviate a lot from the mean. Sometimes we associate this with a Gaussian distribution. That's not the case, or a Gaussian distribution can be fully defined by these, but mean and variance are perfectly well defined for any distribution, right? These are definitions. You do not need to have a Gaussian distribution to have a mean and variance. Sometimes I hear that, but that's not true, right? These are defined for any distribution at all. It's just that the Gaussian is fully defined by those. That's all you need to know, and you know everything about the distribution. But for something like this, just knowing the mean and variance doesn't tell me everything about the shape. Okay, one last quick review item is the cumulative distribution function, so known as the CDF. So if I just draw, here's my PDF, this is the PDF, right? It's gonna look like whatever it does. This is X, P of X. Okay, the CDF, we give it a capital letter, is going to be the cumulative integral. So I can write it this way. It is the integral from minus infinity to some point X, P of X dx. And I guess we could put in a dummy variable, but in any case, so in other words, the value at, say, this value of X, right, is going to be the integral of this curve all the way up to that point. Okay, so it's going to start low, or eventually it starts at 0 if I go infinitely far away, and it's going to increase. So that point here, right, this would correspond to that integral there, right? This would be that integral, and then eventually it's going to go towards 1, right? Because I've integrated the full thing. So it just tells me the cumulative probability. What's the probability of any event that's less than or equal to the point I'm at? Okay, so let's just review. Let's now discuss reliability. Okay, so here's a simple 2D optimization problem. This is called the Barnes function. So there's 3 constraints here. Here's some contours, and this dot here is my normal optimum of this function. It's constrained optimum. I'm right up here against this constraint, and that just is using the normal solutions that we're used to. Okay, so here's what we want to think about with reliability, though. Imagine, as we've discussed, that there's some uncertainty associated with these variables x1 and x2. Even though I want to get this optimum, here's my deterministic optimum, I know there's going to be some deviations, right? Like maybe this is a dimension of my beam, and I know there's going to vary somewhat. And even if the physics are deterministic, even if I calculate the stresses and deflections and so on very precisely, I just know that some of those inputs are going to vary. And so even though I try to design to this point, I could get anything within this cloud of points. And maybe you can imagine this as a 2-dimensional Gaussian, right? So it's more likely I'll stay here, but I could be further away. And it doesn't have to be Gaussian, right? It's just whatever probability distribution. It doesn't need to be symmetric in all areas. This is just a visual, right? This idea, the problem, just like our airport problem of being late, that there is now, because I went right up to the constraints, there's a significant probability that I'm over here, that I actually violate some of my constraints. And then my structure may fail, right? I may exceed the stresses on the structure or the deflections or whatever the constraints are for a problem. There's a significant chance I'm going to fail. So a reliable design is going to incorporate that uncertainty in the optimization and move away from the constraints. Notice there's always still going to be some probability that I would fail, but I get to choose what probability I'm comfortable with. Right? I can't bring that to zero, but I want to reduce that probability of failure to an acceptable level. And notice, and this is the case always with reliability and robustness as well, as we'll see, I have to give something up. I generally can't just get this for free. If I'm going to sacrifice on my sacrifice on the sense of I'm going to, I shouldn't say sacrifice. If I want to be more reliable and not fail, I'm going to have to move away from the best point. So my objective is actually in general going to decrease. So I won't have as good a performance, but it's now reliable, right? And that's ultimately what we need. So we have to give that up. That's understandable, but now it's safer, right? It's not going to fail. All right, so how do we do that? We've had constraints like this, right? That g of x is less than or equal to 0. For a liability problem, we'd change it to something like this. We would say the probability that g of x is less than or equal to 0 should exceed some reliability level. Okay, we call this the reliability level. Okay, and so that's now a design choice that we have. So for example, if I set R to be, just make up a number, 998, whatever, so let's just do nines. Okay, 999, that means that I want my constraints to be satisfied with a 99.9% reliability. That sounds good, and it really depends on what you're looking for. You might search sometime on the internet, is 99.9% good enough? There's a lot of these lists, I don't know how accurate some of them are, but they give you some idea that when you're talking about large numbers, like, the number of cars driving in a given day, or the number of people delivering babies, or the number of mail being delivered, or whatever, if your reliability is only 99.9%, that's actually a ton of failure. So even that isn't very good, but just to give you an example. But this is something we had to choose. And of course, the tighter I make this, the higher probability I want to be reliable, I've got to move this further and further away. So this is not free, right? It's a design choice. What's an acceptable reliability for a given problem, right? I mean, it's going to depend. For like I work in the aerospace industry, we're going to need really high reliability levels. On the other hand, if we're building, like maybe a children's toy, it's not going to be such a big deal if it breaks. And so we may not need such high reliability levels. So it really depends. Well, because it depends what kind of children's toy. If it's a safety, then that's a problem. But if it's a non-safety thing that breaks, then we may not need such a big deal. If it's a bridge versus, a little sign on the road, right? This is a design choice. Okay, so we need to figure out how to do this. And we're going to talk more about that in 2 lectures. I'm going to talk about one method today, and we'll talk about a simplified way to do that. Okay, but I want to talk about a method that you have likely seen, and it's called the first order perturbation method. It's used a lot in experimental measurements. If you've taken a measurements class, you probably did some error propagation, and this is a technique that's often used there. We're going to talk about 3 other techniques that are useful for calculating these statistics, propagating uncertainties, as we'll call it. But this is one that you've seen before. So it looks something like this, that let's say the idea here is that I've got, here's some function of interest. X comes in and f comes out, right? That's just how we're used to seeing it. But this time now, f is not just a deterministic quantity. F has some distribution associated with it. So instead, we're going to pass in a mean and a standard deviation or a variance. Okay. And now what comes out, I want to know not just, I want to know another distribution is going to come out, right? And it's going to look, however it looks, be different potentially. I want to know the mean and the variance of that distribution. We may actually want to know the whole distribution. The method we'll talk about today won't tell us that. It will just tell us the mean and variance, but there are other methods that we'll discuss, like I said, a couple of times, that we can get these output distributions. But this is the type of problem we're looking into. So first order perturbation method is just based off of first order Taylor series. We assume that every input is independent. And we assume that all these input distributions are symmetric, which is not the case of what I've drawn. So this is not accurate in all cases, but it's a simple method. And the mean is really simple, right? It just says the mean of the output is just, you evaluate the function with the mean of the input. That's simple. Okay, the variance is a little more interesting, and this is the one you've probably seen, is that the variance of the output is going to be the sum over all inputs and x of the partial of f with respect to xi times the variance or the standard deviation. So I should xi, we square them. Okay, so hopefully you've seen something like that. If not, now you have. It's fairly straightforward. So these we assume are all known, right? We know kind of our distribution of the inputs. We have to figure that out somehow, right? Either we assume something, we get some data. These are known. We're trying to figure out these things. So these are known. We just have to get derivatives of f, something we've talked about at length. And then we just have this propagation formula, right? So we take derivatives, multiply by standard deviation, square them, add that up for every input. And although I wrote x, these x's could be design variables, but they could also be parameters, things that we're not actually optimizing that still are going to affect our output variances. Okay, so today I want to talk about, so this is a method that, you know, as I mentioned, has some limitations, but let's talk about a simpler approach to use this. If I wanted to do this in optimization, I would need to get derivatives, which we're used to, but then I would calculate these at every iteration in the optimization. And then these would become things that we could do to change our constraints. But I'm going to talk about a simpler approach where we actually do all that calculating of statistics outside of the optimization. And this only works for constraints. It only works for reliability problems. If we want to do with the objective, we can't use this approach. But this is just sort of our more gentle introduction. We're gonna keep this a little simpler first. And this can be effective, right? Because sometimes that's all we need, is just we need something that's more reliable and we're not as worried about the variation of the objective sometimes. Okay, so here's the simpler approach. Remember, this is our what we wanted to do. We want to calculate the probability that our constraints are satisfied and make sure that's satisfied to some level. If all the conditions that I already talked about, independent and so on, and we add one more assumption, if it's normally distributed, if every input is normally distributed, which is an assumption we often do if we have no other information, right? If I didn't know something about the input distributions, we often assume that they're Gaussian, and so we just have to specify a variance because the mean is the value, the normal value that we're used to using. We just need to add one variable, the variance. So in that case, we could write our constraint like this. Instead of g of x is less than or equal to 0, we're going to write g of x plus k times sigma g is less than or equal to 0. I'm adding a bit of a buffer here. Okay, it's almost like a safety factor. I mean, safety factors are actually derived using kind of these ideas, statistics, and then we boil it down to a number. But this is going to be a bit more rigorous, especially where in places where safety factors are not going to exist. So I need to calculate my standard deviation in G, and I'm going to decide, K here is basically, well, not basically, it is related to this reliability level. Okay, so if I put in, you know, 1 standard deviation versus 3 standard deviations, I'm pushing away from that boundary further and further. So K is something that we decide. So for example, K comes from that CDF. So here's my CDF. Here's well, I guess we could just draw it from the PDF. It doesn't really matter. Here's the PDF, and here's a normal distribution, right? And so if I've got, let's say k equals 2, that means that's the area all the way from under here. And yeah, this is easier from the CDF, but just to kind of show you that integral, right? That probability is not 95%, because 95% for the normal, that's the area if I did not include this part, right? It's kind of -2 to -2, but I'm going from -infinity to 2. So the probability here is actually one-sided. It's 97.72%. So in other words, if my reliability was 97.72, that would correspond to a K of 2. It's basically saying, because my constraint is one-sided, right? It's just saying probability that I would fail is going to be, or this can be reliable, is going to be related to everything under here. This is my failure side. We often will also have to choose K based on considering my overall reliability. I'll show you an example of that in a minute. But for example, if I had 2 constraints and I needed each one of the constraints to be, say, 97.72% reliable, then my overall reliability would be the product of those. So I have to be careful that, for example, if constraint 1 is going to fail at 90% probability and constraint 2 is going to fail at 92 or at 90% probability, then my overall probability of failing is 0.9 times 0.9, which is 0.81. So I have to think about that, what I need for each individual constraint if I have some overall reliability I'm trying to get to. Okay, so here's the simple procedure that you can use to not propagate uncertainties in the optimization. That's something we're going to do later, but if all I have is constraints, this is only for constraints, I could do this procedure. Okay, 1, just deterministic optimum. That's what we've been doing already. Just optimize like normal. Okay, then at the optimum, I'm going to compute the standard deviation of G. So now I'm at a fixed point. I'm at X star. I'm not propagating this through this optimization. I'm just calculating it afterwards. Now I adjust the constraints. This is a linearization. So I may need to repeat, right? Because this is just an approximation. So I may need to repeat this, but often just a couple times is enough. Okay, so let's do an example, and this will be the last thing for today. So here's an example, just a simple problem. Few variables, got an objective, couple of constraints, and here's the optimum. Just using all the methods or any of the methods we're used to already. Okay, so let's try to use this approach that we discussed. So let me share my screen. I'm just going to do this here in MATLAB. Switch to desktop. Okay, here we are. So I've already set up the basic optimization because you should be familiar with how to do this already. If you're not using MATLAB syntax, that's fine, right? Just basic idea here. Here's my objective. I put in the gradient, and here are those constraints. I had 2 inequality constraints. There's no equality constraints. These are the derivatives, the Jacobian of my inequality constraints. So those are my functions, my constraints. I've got a starting point, lower and upper bounds, and I told the optimizer I'm providing derivatives. Okay, so all stuff we've done before, and I'm just going to run it, and I get a solution, and that's the solution I said was deterministic optimum. Okay, so let's now assume that each of these inputs is not actually going to be exactly 1. That's what I'd like them to be. I'm designing them to be 1, but let's say they're normally distributed. The mean is 1, but they have some variance. Let's say the standard deviation is 0.1, and we'll just make it the same for all 3 just to be simple, right? They could each be different. There's not, that doesn't matter. But we'll say they're each just have, a standard deviation of 0.1. Okay, well, let's see how often my constraints would fail, right? If I evaluated my constraint function at xopt, I should get, I should get zeros. Let's see what I get here. So I just want G, okay, the other outputs here. So I'm just gonna length them out. Now I'm going to display G. Okay. What does display do? I don't know. Switching language too many times. Yes. Okay, so there are my constraints. So the first one is active here. I can't write it out. It's basically 2 times 10 to the minus 6. So it's within my tolerance at 0. This one is not active, but my first constraint is active. I'm basically right up against that first constraint. I can't print it here because this isn't a function, so it's not being saved. Okay, so that's great. That's what I wanted. They're all less than or equal to 0, but now I'm assuming there's some uncertainty. So let's see how often these constraints would actually fail. So let's just have a bunch of samples. Let's say I do this 1,000 times. I'm just going to randomly generate numbers from that normal distribution, calculate my constraints, and just count how many failures I had. So let's say I've got 0 failures for now. I'm going to run this 1,000 times. And every time I do that, I'm going to create a variable that starts at the mean of the optimal solution. And then I'm going to add a normal, this just tells me to generate 3 random numbers. I'm going to generate a random number sampled from a normal distribution. That's what rand n is. Instead of sampling from uniform, I'm sampling from the standard normal, which means mean 0 and standard deviation of 1. So I need to multiply it by the standard deviation that I want so that it has standard deviation of sigma. So this is generating 3 numbers, right? I just made them all the same for each 3 variable, but they don't have to be. Okay, so now I want to evaluate my constraints with this variable that's going to be randomly generated, or it's going to have some, variance because of that random distribution. And I want to see if any of my constraints are positive, meaning it's failing, then I'm going to increment my failures. Okay, and at the end here, I just want to see the percentage. So I'm going to write failures over the number of samples, see how often I failed. Okay, so that's pretty bad. It failed over 82% of the time. With that kind of standard deviation, this is not a good design, right? It's too aggressive. So let's use the procedure that we just saw. I've already solved the optimal solution here. And by the way, I should have said this before. You can still back up and go do the actual problem. It would be good for you to try this first before I do it, but I'm going to do it now. So you can pause and go back if you'd like. But so let's go back in, or let's do this. So first thing I need to do is let's put a few comments here. This is count failures. Okay, so now I want to compute sigma g, standard deviation of the constraints. I have 2 constraints, so I'm going to have 2 standard deviations. So I know the standard deviation of my input. I guess I could call this sigma x. Be a little clearer here. They're all the same. So I want to figure out sigma g. So I have to go back to that first order formula. Remember, the formula was I take the gradients and I multiply by the standard deviations of x, square them, and add them up. Okay, so sigma g is going to be, there's 2 of them because there's 2 constraints. So let me just go through each one. And then for each one, I've got to do a loop across all x's, and there's 3 x's. So sigma g I is going to be sigma gi plus, it's the derivative of f with respect to x. So I need to grab those things. I've got them here, so I'm just going to call this function at x opt, so I can get my gradients. Actually, it's not f I need g, sorry. So I need this one. Okay, and all I need is, in this case, is I need the Jacobian of my constraints. Okay, so it's going to be, this is with constraint I with respect to xj, I think. The way I did it. No, see, I transposed it because MATLAB wants it the opposite way. So yeah, because MATLAB always wants to transpose, so I have to flip that. And then the formula is to multiply by sigma x. And we take this whole thing and we square it. Sorry, this is sigma x associated with x is j. And then I square this whole thing, and then I add those up. Okay, so hopefully I did that right. And that gives me, that actually gives me the variance, so I need to take the square root. Sigma g is the square root. Okay, and let's just run that real quick. Looks like I messed up somewhere. Index exceeds the number of elements. It's not in a function. Actually, do I have to have it in a function? I may not have to have it in a function anymore because it used to be that. Anyway. Okay, now I can inspect that. What does JG look like? Okay, it's 3 by 2. So yeah, I have it backwards here. So constraint I, let's see. So the columns are the constraints. No, actually, this seems right. Index exceeds the number of array elements. Sigma G I, that's right. That's good. And sigma X. Oh yeah, that's the problem, right? Sigma X, I should have made it. I mean, these could all potentially be different. But they're all the same. So in general, I need to index into the jth one. So actually, we can just fix that. So we can show you a more general case. Okay, so they could all be different. And in this case, I have to fix this. Not times. All right. Okay, so there are my standard deviations and my constraints. All right, so that's done. Now I just need to change my constraint. And so the formula that we saw was that the constraint was going to become, I'm just going to kind of write this, instead of g is less than or equal to 0, we're going to make it g plus k times sigma g is less than or equal to 0. So we already have sigma g. We now need to find k. And so in the problem, I said we needed an overall reliability. What did I say? I made up some weird number. I actually didn't write it on there. Or I didn't show on the screen. Yeah, it was 99 point, I made up a weird number, 99.5956. And the reason why I made it up is because it gives a nice value of k. So k is, let's see. Let's look up this function. There's a function called norm inverse. Normal inverse cumulative distribution function. So it's the inverse CDF for normal distribution. Okay. So I just give it the probability that I want. And I have two constraints. Right. So I need my overall, let me just write this. Overall reliability of 99.5956, this weird number. Okay, that means my reliability is going to be the reliability for G1 times the reliability of G2, assuming they're independent. And so I need the reliability of one of those, right? Let's assume they're the same. The reliability of this times the reliability of this equals this. So in other words, the reliability of one of the constraints is the square root of this. Okay, So that's going to be for one constraint. So let me just write that. The reliability of G is the square root of 995,956, which is this bigger number, right? Which should make sense that if I want my overall reliability to be something, I need each constraint to be even more reliable, because the total probability of failure is multiplying the probability of every constraint, right? Because any one could fail, and that would be bad. Okay, so I need each constraint to have this reliability, and I'm going to use that function. There's also, if you have other distributions, there's something in MATLAB and in every language. It's kind of different names. This is called an inverse CDF, sometimes called a point percentile function or quintile function. Anyway, I could use this one too. I could give it the normal. I'm just going to use the function that's specifically designed for normal. It's just a shortcut. And then I'm going to give it RG. And so this is going to tell me the K value. Guess that wasn't such a nice number. Oh, you know what? Yeah, I know why. Anyway, it's not a nice number, but that's what it is. It doesn't matter. It's not a nice number. That's the K value that I need. So that's looking up the inverse CDF, basically telling me how many standard deviations away from the mean do I need to be to get that reliability. So I need to be 2.87 standard deviations away from the mean to get a reliability of this number, 98%, 99.8%. All right, so I have everything I need to modify my constraints. So I'm just going to create a new constraint since I'm going to leave what I have there since I'm using it. I just need to add this K sigma G, and I've already got all of those. This is where I'm going to need to put it back in a function because I'm using variables from the outer scope. So I'm going to put this back into the overall function so that I can use variables inside. So it's going to use this K, this sigma G. All right. So almost done. Let's re-optimize with the second constraint. And when I do that, I also want to now see how many times I've failed. So let's see how many times I've failed with this new solution. Yeah, whoops. Sigma G is there's one for each constraint, so I'll add it like that. There we go. Okay, so first of all, let's see what happened. The optimum originally was 5.38. Now it's much higher. I had to sacrifice some performance. But my reliability before, remember the number of failures. The number of failures I had was over 81% failure rate. And it's going to be random, so it may not be always exactly the same. You know, I'd have to get a big number to get this converged really well. But now my failure rate is 0.2%. And ideally, that number plus this should be about 1. Oops, I need to convert that one to a percent. Well, no, I messed it up. The answer divided by 100. Oh, it's already a percent. Oh, yeah. Yeah. So 0.99. Oh, yeah, it's saving the wrong thing as the answer. That's why. Okay, so let me put out more digits so I can see it. Okay, so there's my failure percentage. If I add my overall reliability that I'm trying to get, should be close to 1. It's pretty close, not perfect. And that's in part because I'm only running 1,000 cases here, right? Because every time I run it, you can see this number is actually going to change. It's not super exact. I'm trying to resolve this really teeny number, so it's hard to get, but you can see I'm in that neighborhood that I should have, you know, with 99.6% overall reliability, I should have about 0.004, less than that, failures. So I'm getting there, right? So the takeaway we should see from this is that I didn't actually have to really change much from an optimization standpoint. I had to do all the uncertainty propagation outside. So that made things easier. Because normally what happens is that if we propagate these inside, which we will talk about later, I had to get these derivatives, but then I'm going to need derivatives of the derivatives because these derivatives are being used to calculate my constraints. Right, this number goes into my constraints, and later I'm going to need derivatives of my constraints for the optimization. So that can be expensive with this, or that can be challenging potentially. Certainly more expensive as we propagate uncertainties. But this approach is very inexpensive. Basically, we solved the problem, figured out our uncertainties, and then forced it a couple standard deviations away, depending on how reliable we wanted to be, resolved it, and that was it. Like I said, we may have to iterate a couple times because this is just a linearization, but it tends to work pretty well. Okay, that's it.